Now this is an example of a metric tensor transformation, and we're going to try to give a basic understanding of what the Christoffel symbols do. Well, step 2, we define the original metric. We'll use a 2D Cartesian, which is xy coordinates, with a simple flat metric given here. This is Euclidean flat space, so indices mu equals 1, 2. And now the goal is to transform to polar coordinates r theta. Now step 2, we define the coordinate transformation. X equals r cosine theta, y equals r sine theta. The Jacobian of this is this. It's a partial derivative matrix. So this is x with respect to r. So this is x here with respect to r, so we're just differentiating with respect to r, so that will leave us cosine, which is here, and so on and so on. So this is after the transformation. We will end up with this matrix. So here x to the mu equals xy, and x prime to the x prime alpha equals r theta, our polar coordinates. And you'll see x prime alpha here is on the lower part because we're differentiating with respect to that. Now our metric transformation formula, the transform metric in new coordinates. This is step 3, where our new prime coordinates is this after undergoing these transformations. Now since G mu nu is the Kronecker delta, which is the identity matrix, this gives the form here, where these are the Jacobians, and our metric is the Kronecker delta, which is when if alpha equals beta, no, if mu equals nu, then it's 1. If mu does not equal nu, then it is 0, and that's what the Kronecker delta is. So we compute the components in step 4 here for our metric components. So g prime r is given here, which is cosine squared plus sine squared equals 1. And now we go through g r theta, g theta r, both primed, and we get the same form here, which after undergoing some multiplying out a little bit of algebra, we can see that these cancel and we get 0 for these, which is here, and we will see up here where r theta and r theta and theta r are 0. So and now we will get a g prime theta theta, which equals minus r sine squared plus r cosine squared, which we just pull the r out of this, and sine squared plus cosine squared is just 1, so we get r squared. And now the step 5, this is our new metric in polar coordinates. This is the familiar polar metric given here. Now with step 6, we compute the Christoffel symbols, the Levi-Civita connection. We'll use the formula here, but to give an understanding of what this is, say if we were transforming between polar and Cartesian, then like if we have a symbol such as this, r theta theta, the theta here would be the output of the vector, and these ones here would be the basis on what we're differentiating with respect to. But there is a basic formula for this here, which we'll be using this. Now we compute the inverse metric, which is simple. It's just inverse. The non-zero derivatives are all given here, and the only non-zero derivative is 2r. So we compute some non-zero Christoffel symbols by plugging these in here, and this is the inverse from the inverse metric. Yes, So then after we've computed these Christoffel symbols, we'll see that r theta and theta I are both the same. And our summary of what just happened here is that the original metric G mu nu equals I, the identity matrix. The coordinate changes x, y goes to r theta, and the transform metric G prime alpha beta is 1 0 0 and r squared. The non-zero Christoffel symbols are here. And the conclusion is that we have shown how tensor components change under coordinate transforms, and how Christoffel symbols encode the curvature due to coordinate choice, even in flat space. And that's the end of this mini lecture. Please do subscribe.